All right, so then for chapter 10, we are going to talk a little bit more about some rotational motion, and in this section, we're going to get into something called rotational inertia as well. For now, let's just do a quick review of kind of our rotational kinematics, right? So again, we just have something that is traveling in a circle, right? We have some little object right here. It's moving along in this way or whatever, right? So this circle, the circular path that it has, right, has some sort of radius and it has covered some sort of arc length around this thing, right, as it moves, right, some sort of arc length delta S. So now, unlike in chapter 6, which is where we kind of first looked at this stuff, we are no longer constrained to just moving at a constant rate. So it's circular motion, but it's not uniform circular motion, right? We're going to have objects moving in these circles, but now we are allowed to have them accelerate. We're going to use that tangential acceleration that we have kind of briefly talked about before, but not really used a whole lot. So if you remember, right, we can say, right, we have this angle theta here as well, right? So we have our angular kinematic qualities, very analogous to our linear kinematic qualities. So we have our delta theta, right, kind of our angular position, right, how far around this circle we've gone. This can be written as delta S over R, right, the linear length divided by the radius. We also have our omega, which we can write as v over r. This is our angular velocity. And if we do this, right, we can take our linear velocity, right, just how fast we're actually covering the distance around the circle, divide that by the radius, and that gives us our angular velocity. And this is all, again, of course, in radians, right? This is why working in radians is very, very useful and easier. There's no other extra unit conversions I have to do after this. So just v divided by r gives me my radians per second, right? So this is radians per second. And then as we said before, we also have our alpha, right? This is our angular acceleration, which is related to our tangential acceleration divided by r, right? So again, the tangential acceleration is how the speed is actually changing, right? So we had our centripetal acceleration. We spent a whole chapter looking at that. Our centripetal acceleration is just the acceleration associated with the fact that we are changing direction as we go around this circle. Whereas again, the tangential acceleration is associated with the fact that our speed changes, right? Now we are allowing our speed to change. We are not undergoing uniform circular motion. We are allowing this speed to vary. Okay, so we have all these different quantities, right? Our angular position, our angular velocity, and our angular acceleration. As you notice, they are all the linear quantities, but divided by r, right? We have delta S divided by r, we have v divided by r, and we have the tangential acceleration divided by r, right? And so this actually does result in the fact that we have very similar kinematic equations, right? We have rotational kinematic equations, just like we had our linear kinematic equations. I can also write this. I can say delta theta is equal to omega naught times t plus 1/2 alpha times t squared, right? This looks very familiar to you. Instead of having our delta x is vt plus 1/2 at squared, we have delta theta is omega t plus 1/2 alpha t squared, right? But that same relationship still holds, right? We've basically taken the entire equation and we've just divided the whole thing by the radius of the circle that we are traveling around. So of course, with this, you have this kinematic equation. This one is valid. We also have our omega as a function of time. It's just going to be omega naught plus alpha t, right? As this object, maybe it's, we're straight into the circle, but we can speed up, we can slow down as we do so. And then we also, of course, have our omega squared equals omega naught squared plus 2 alpha delta theta. So all of these relationships between these angular quantities actually still hold, right? And you can do all different kinds of kinematics problems with just from an angular perspective, right? With where you have your angular quantities instead of your linear quantities instead, right? So all the problem-solving methods that you've used, you can actually apply, and you can do rotational kinematics problems manipulating these equations in much the same way. Again, the way you solve them is largely similar, like the actual mechanics of the algebra that you have to go through. But make sure you do understand the visualization difference, right? The actual physical situation is different. This is applying to when we are moving in a circle with some radius r, right? We're just saying that we are now allowed to speed up and slow down. So yeah, so this is kind of just a little bit of a review. I'll probably ask you some questions that deal with this. We're not going to go too crazy. We've already done a lot of linear kinematic stuff at the beginning of the semester. The angular kinematic stuff is very similar. It's important to understand it conceptually, but I'm not gonna go too crazy with doing the angular kinematics problems like we had with the linear kinematics problems. So yeah, so this is kind of our basis, though. We need to make sure that we are familiar with this so that we can kind of use it to do other more interesting things, right? Okay. So let's move on. Now let's kind of get to this idea of our rotational inertia that I talked about before. Before we get to that, though, we need to kind of discuss forces acting on these things, right? So again, we have some object traveling in a circle, right? When we have all our quantities. But now we're going to say, what happens when I actually do apply some sort of net force on that object, right? So I'm going to apply it in the same direction that's moving, so the direction of the force is going to change, right? So again, you can imagine this as, I don't know, say this is like a merry-go-round or something, and you're running along next to it, and you're applying a force to push that merry-go-round in this circular motion, right? So let's kind of do this same type of analysis, right, that we had before, but kind of see what our equations look like for our forces when we look at the rotational cases that we have. Well, what do we know is going to be true? Obviously, we have this, F net equals ma, right? We know that that must be correct. So if there's some little mass on the end of this here that we're pushing around like that, what do we end up with? Let's say that we just, in this case, we'll make it even simpler, right? We're just going to say that we have some sort of mass, right? This little point mass here moving in a circular motion, right? So we don't even have a merry-go-round. We don't have a disk or anything like that. We just have a point mass that is moving in a circle, and there is some force kind of pulling it around, causing it to accelerate as it goes around in this circular motion. And what can we say, what we end up being able to write about this? So we know that F net has to equal ma, right? This one just has to be true. This is just simple Newton's second law, but we can actually do a little bit better than this now, right? We can actually start to write this now in terms of our net torque, right? We can say this. We can say R times F net equals R times ma, right? This, of course, is then our net torque, right? Just this radius. Again, we're saying that our net force is just acting perpendicularly, so this is okay. So we're just saying our net torque is then equal to R times m times a, right? Okay, so we're getting somewhere here. Let's replace this a, though, right? We're still talking this a is still our linear acceleration, right? This would actually really be our a tangential that we're referring to in this case. So let's instead replace that with our angular quantity, with our angular acceleration. What do I get when I do that? Right now, my net torque is equal to R times m times R times alpha, right? If you solve for this this tangential acceleration in terms of r and alpha, right? It's just r times alpha gives you the tangential acceleration. So we can kind of combine this a little bit, and we can rewrite this, and we'll start to see an equation that looks very familiar, right? So of course it should, because we started with it up here. So we now have our net torque is equal to m r squared times alpha. Now this is a very important result, right? We started with our linear Newton's second law, but what we have ended up with, we can see that we can derive a kind of analogous rotational version of Newton's second law. Here we have F net equals mass times acceleration. Here we have net torque is equal to some quantity here, this mr squared, times angular acceleration. So what is this term here? Again, this is kind of like our angular force, right? It's not exactly right. It's a little bit different, but it plays a very similar role. Torque plays a very similar role in this angular case that force does in the linear case. So here we can say this is kind of like our angular force. We know that this is actually just angular acceleration. Right? It's not like it. It just is the angular acceleration. So what does that leave? What is this quantity? It's actually a very important thing to understand. So again, we have this nice analogous equation, right? It's not F equals ma, but it is torque equals something, this mr squared, times alpha, right? So this is kind of, this mr squared value that we have is very interesting. And the reason it's very interesting is because it's not mass, but it is something that's going to be called rotational inertia. So what is inertia, right? When we talk about linear inertia, right? Inertia is kind of mass, like a measurement of inertia, right? In some sense, basically, when an object has inertia, right, it's just more difficult to, you have to apply a force to speed that object up or down, right? If you want to do that, right? So what we're saying is objects with higher mass, right? They have more inertia, right? It's more difficult to change what they're doing, right? So now what we're saying here, this quantity, right? We have our analogous um, angular force here. We have our angular acceleration here. This quantity mr squared is actually playing the role of rotational inertia, right? So it's saying the bigger that this quantity is, the more difficult it is to start speeding this object up. It's spinning it up faster and faster or slowing it down faster and faster. So what do we really have here? What's going on conceptually? It's kind of a little bit tricky to think at first, but it's really important that we understand this concept of rotational inertia. This quantity here, mr squared, for a point mass, right? Make sure we understand that. We're going to have different ones of these here in a second. If we have a point mass, we have a rotational inertia of mr squared. If this mr squared value is higher, what that implies is that we need a higher torque to get the same acceleration, right? Or if it's lower, we can have less torque to get the same acceleration. Just like we have the same relationships with our force equals mass times acceleration, right? If you have more mass, you need more force to produce the same acceleration, right? And so on and so forth. But now what we're saying is we can actually increase our rotational inertia in two different ways. Obviously, if we have more mass, it's more difficult to get this thing moving. Okay, sure, right? If our little point mass here that's going around in a circle, right? If it's 1 kilogram, you can just, maybe give it a little push and it'll start spinning around. Or if it's like 100 kilograms, right? It's going to take some work. It's going to take some effort on your part to really get it spinning up in the same manner, right? But there's something else we can do. We can also take that mass and we can move it further out, right? So here, this is some radius r that this mass is away. But if I want to move this mass at the same angular acceleration, but it's further out, that's going to be much more difficult. And this should kind of make sense to you, right? So the r can also be bigger, and that will give us more rotational inertia, right? If I just move this mass, if I try to move this mass around a larger radius circle, what's really going on? Well, if it's moving at the same angular rate around a much larger circle, right? So if I have two objects here, right? Let's say I have one object here that's going around this way. Let's say I have another object here that's going around in this way, right? If I accelerate them at the same angular rate, right? But this one obviously is at a much further radius away, right? Over some, let's say they accelerate around the same angular diameter, right? All the way around to here. Obviously, if they're accelerating at the same angular rate, right? This one's actually accelerating much, much faster, right? The actual linear acceleration that you would look at, the actual speed that is associated with this, it's going to be moving much faster since it has a much larger distance to cover, right? So if you want to maintain for something further out at a further radius, right? Even if they're the same mass, this object that is further out, it has the bigger r, it will have more rotational inertia, and I will need a much larger torque to get this object moving at the same angular acceleration as this object, right? So again, this rotational inertia thing, it's kind of tricky at first. It's weird. It's like I have like angular force, I have angular acceleration. So is this like some sort of like angular mass? Like what does that really mean? It's a little awkward. Rotational inertia, I think, is a very good term to describe it though, right? The rotational inertia, this is the measurement of how difficult is it to get your object to either spin up or spin down, right? To speed up while it's rotating or to slow down while it's rotating, right? And actually, we're going to see, right? This is, as I stressed, this is for a point mass. But what if I have a different shape, right? What if I actually did have this merry-go-round disk? Well, that would be a little bit trickier, right? So in general, right, for a point mass, mr squared will be the rotational inertia. But for different shapes of objects that are spinning, we are going to get different rotational inertias, right? But all the time, every time that we do it, it will still be based upon how much mass we have and kind of where is that mass located, right? What is the shape of the object? So let's just do a quick example so we can kind of see exactly what we mean by this. Let's say we have the shape of our object is like a dumbbell or something like that, right? It's actually going to be similar to the shape that I just drew on the other page. So let's say the shape of our object is something like a dumbbell, right? So I have a mass here. This is mass 1, and then attached by a massless rod of distance r, I have another mass over here. And I want to take both of these objects, right? And I want to spin them around a circle like this. So it's going to move as one rigid object, kind of like a windshield wiper or something as it goes around, right? So this is a distance r. This is also a distance r. So this one is rotating around a circle of radius r, and this one is rotating around a circle of radius 2r. So, and I'm going to treat them as one object though. And what I want to do is I want to calculate the rotational inertia of this total object, right? So the rotational inertia of this object here, we know would just be mr squared, right? It's rotating, it has a mass m. The radius of the circle it's moving around is r. This one, the rotational inertia, would be m times 2r squared, right? The overall radius now is 2r, so it would just be 2r quantity squared. So you'd actually do it like this. You could say you have to go around, you have to add up all of these, right? So actually the symbol that we're going to use for rotational inertia is I. Should have mentioned that earlier. Rotational inertia is abbreviated with an I. And the way you can calculate I for various objects is this way, right? You go around to every bit of mass. You say how much mass is there. You say how far away is that mass from the center of rotation. And then you add that to every other spot that you have. So you just sum up all of these. So don't worry about it too much. I'm not going to make you do this. We just need to understand it conceptually. I'm not going to have you calculate any of these, I don't believe. But we do want to do this, right? So in this case, we'll just show this very simple example where we have a point mass here and a point mass here. It becomes very easy to do. We have mr squared plus m times 2r squared, right? So overall, my moment of inertia would be mr squared plus 4mr squared. My total moment of inertia would be 5 mr squared, right? This moment of inertia actually gets 5 times larger by doubling the mass, but putting it further out, right? If I just double this mass here, and I don't have this one, then it would just be twice as high, right? I just have 2mr squared or whatever it happens to be. But yeah, so this is how you'd have to do it for these individual objects, right? So if I have this object here, it's kind of like this dumbbell, right? We have a massless handle or whatever, a rod between them. We have a bunch of mass here, we have a bunch of mass here. The overall moment of inertia, the overall rotational inertia, I should say, is 5 mr squared. Obviously, though, we don't always have these nice discrete chunks of mass, right? So again, what about the case of a disk, right? What if we had a merry-go-round disc, right? So we have it here. This whole thing is one flat disc. You can either view it like a merry-go-round or like a CD or something like that, or like a record or whatever it happens to be, turntable in your microwave. Any sort of disc-like shape that is rotating will kind of all be described by this. What would this moment of inertia be? So what you'd have to do is you'd need to use calculus, right? You need to go all around to all of these individual spots everywhere on this disk that we have and calculate every single one, right? Add up all the little bits of mass, add up exactly how far away they are. And when you do that, again, the method to do this is actually calculus, which we're not going to do, so I'll just give you the result. When you do that, what you get is a moment of inertia of I equals 1/2 m r squared, where m is the total mass of this object and r is the radius of this disk, right? So it actually ends up being 1/2 mr squared. Why would that be? Well, again, for a point mass, right? We can kind of visualize it like this. We have a point mass going around like this, right? We have, here's our mass, here's our radius. I just equals mr squared, right? So we have just one bit of mass at this point out here at this outer edge. So the moment of inertia, the rotational inertia, sorry, getting my terms mixed up. The rotational inertia is just mr squared. Whereas in this case, right, this mass is kind of smeared out, right? We have some mass out here at the edge, but we also have some mass here at the center, right? And obviously, if we have more mass at the center, then we get a smaller rotational inertia. So by taking this mass and kind of smushing it out and having some of it be closer in, you actually end up with having a smaller overall rotational inertia. That's assuming, of course, that the mass of these objects is the same and that the radius is the same. Of course, you can mess with that, right? If you have just like a little marble on a string versus an entire merry-go-round, then obviously the merry-go-round will still have a higher rotational inertia, right? So yeah, so this is the rotational inertia. This is the value that we'd always use anytime you have a disk, right? Any sort of disk-like shape that is spinning around, this is the moment of inertia that you would use. You'd use 1/2 total mass times the radius of that squared. If you have a sphere, it turns out to be a little bit different. If you have a cylinder, it becomes different again, right? All these different shapes have different moments of inertia. I'm not going to ask you to memorize any of these, but it is important that we understand why they're different and where they all come from, right? Actually, and I'll make sure I don't have it, I'm not going to put it in the video itself, but on the same page as this video, if you look right below it, I should have attached a picture of various shapes. The disk will be on there, the plate mass will be on there, various shapes and their moments of inertia. It's also in your book, but it's just a good reference point. You can always look up the different moments of inertia for different shapes. I'm not going to have you memorize them. But again, it is important to remember conceptually what this is and where it comes from, right? We need to understand that. So we have this rotational inertia conceptually is, again, it's like our angular mass, which seems like a little bit awkward thing to say, but it really is a measurement of how difficult it is to have something start to spin up, right, or to slow down in either direction, right? And in this case, it's not just based upon the mass, but it's also based upon the shape of the object, right? How is that mass distributed relative to the axis of rotation? Okay, so one quick thing I'll do before we finish this section, we're getting to the next sections of chapter 10. So far we have this, right? We've derived all of our kinematics. We have our net torque equals I alpha, right? Instead of we have F equals ma, we have net torque equals I alpha. The next things that we're going to do in this chapter are going to be rotational kinetic energy and angular momentum. So L is what we use for angular momentum. Rotational kinetic energy, though, right? It is another form of kinetic energy. Angular momentum is a little bit different. It's always kind of a different concept altogether. We will still see some of the same rules apply that we did when we talked about linear kinetic energy and linear momentum. Let's talk about this before. So now that we know, right, we're kind of deriving all these analogous rotational quantity relationships. What do we think our rotational kinetic energy would be? As it turns out, I'll do the full derivation for you, but as it turns out, the rotational kinetic energy of some object, right? Because you can imagine if this disk is spinning, it has, these are moving particles, right? They have mass, they have a velocity, so it will have some sort of kinetic energy associated with it. And in this case, what you get is, instead of 1/2 mv squared, what we get is 1/2 I omega squared, right? And this actually ends up having the same units as energy. This is just another energy that we will incorporate into our conservation of energy problems. Angular momentum, right? Instead of m times v, it is going to be I times omega, right? So I'll kind of show you in the next section where these come from and what kinds of different problem-solving things we can do with them. But for now, the main takeaway that we need to understand all of them is where does this I come from, right? This rotational inertia, and what does it mean? So make sure you understand that, and you should be good to go.